Hey, welcome back. We have one last project for computational mechanics. Then after that, if you want to go back and work on previous work and revise, great. Otherwise, there's Module 5 to look at kind of a combination of Module 3 and Module 4, where you're doing differential equation solving, but now it's like boundary value problems and that kind of stuff. But for today, we're taking a look at Module 4 project. So it's linear algebra and directly applied to finite element analysis. This is like simplest way of setting up finite elements where everything is just a two-dimensional beam and the beam can stretch or compress. It's not going to give you answers about like buckling or anything like that, but it's a pretty good intro to like what's going on in the background when you click solve in an FEA routine. What are we working on so far for finite elements and some linear algebra? I can check in and see if there's individual questions and then come back up, kind of go through at least some of the main tripping points or questions or discussions that kind of come up. Okay. Okay. So as we're like in the first question, kind of coming back to like question 1 in homework 4, it's like one condition number is just of K as a whole, and the other one is like a subset of K. This is the same exact problem that we ran into with those like springs, as we're compressing springs together. The only difference is now the springs are moving in 2 dimensions, so we end up with, instead of a 4x4 or a 5x5 matrix, like 14x14 size matrix. And here, if we look at like if we just have a triangle, my stiffness matrix is going to describe like if I take any one of these nodes and move them in any direction, how much force does it take to do that? So if I know all the displacements, I can calculate how much force it took to create that. So naively, I could just say, all right, I've got 2F going down, and then I have F going up, and some of the forces is 0, like it's not going to move anywhere, but there's an infinite number of solutions because I could keep, and here let me label these 1, 2, and 3. I could say node 2 moves nowhere and node 1 and 3 move up. Or I could say node 1 and 3 move nowhere, node 2 goes down. And all of them are solutions that are equally valid. So it's not that there's no solution, it's that there's an infinite variation of all sorts of different solutions on here. So when I look at this like U, I have a U1x, a U1y, U2x, U2y, U3x, U3y. But I don't want to solve for all of those independently. I got to give it some boundary conditions so that I have one solution. That's the goal. So one way to do that is I get rid of these applied forces and turn them into reaction forces. So I'm taking node 1, saying, node 1, don't go anywhere. You're going to be 0. So a 0 and a 0. And then now at this point, if I apply that force down, there's got to be some force on node 3 pushing up. So I'm going to say, all right, node 3, you can move left and right, but you can't move up and down. So node 3y turns into a 0. So now in this case with just that triangle, I'm only solving for 3 displacements. So U2x and U2y, so how much it moves down and to the right, and then U3x, how much it's going to move over to the right. So this big like K11, K12, K13, 4, K1, K16, and I guess it's symmetric. So the only things that I care about in this case are just too far. The stuff in here, U2x, I guess, yeah, U2y, U3x. And by like by adding that subset of saying like, all right, there are certain nodes where I know what the displacement are, that subset is creating boundary conditions. So when we're trying to figure out like what is the difference, why is the condition number so large for just K? It's because it has no boundary conditions applied versus that subset now has 3 boundary conditions that U1x and U1y can't move and U7y can't move up and down. Yeah, so we're taking an infinite number of solutions, turning it into just one. There's only one solution. And that's like the getting started there. And then some other information that no one asked for. It's in, like, it does say this, but sometimes it helps to actually hear that it's important. Units, at least like the default units that I was expecting everyone to use are newtons and millimeters. So when we look at length, it's all millimeter. Look at force, that's all newtons. And then stress and modulus is a newton per millimeter times millimeter. What's a newton per millimeter squared? Sorry? Megapascal. Yeah. MPa. I like, this is a nice like consistent set of units to use with finite elements in general, depending on what you're working with. I used to do like nanomechanics FEA results, and that one I would use like newtons and nanometers, and then I would end up with like gigapascal units, or no, nanonewtons and nanometers. But megapascal is good. So when you're plugging in, like E is 200 gigapascal, it's 200 E3, not 200 E9 for these results. If you think I'm crazy and you don't like this unit set, if you want to jump into like American units with like pounds and inches, PSI, KSI, just make sure you convert this K matrix, because K is in 1 over millimeter. So EA times K gives you a newton per millimeter. So it's an actual stiffness matrix measured in newtons per millimeter. Because E is newton per millimeter squared, A is millimeter squared, K is 1 over millimeter, so overall you get newton per millimeter. And to get, again, it's a big old matrix telling you how much force it takes to move any node in any direction. All right, and then the other information that no one asked for is there's this link to extra FEA material. This one shows you, it has like a little bit more information about where that stiffness matrix came from, like why it looks like that and how it got assembled, but also it has an example of coming back up. Yeah, so coming back to this one, like looking at a truss, we can actually look at that triangular truss as it deflects. So if we apply a force to it, we can look at how far all the nodes moved and what the reaction forces were. And if we can do it for 3 nodes, we can do it for 7 nodes. So assembling that K matrix, solving for all the U values, and the last plot that is in that extra FEA is like this. It shows all the node displacements and all the reaction forces. So we have applied forces are all in these red vectors. Those are the only external forces. And then all these blue, all those blue, what am I thinking of? Blue arrows. That's how much displacement each node had for that amount of force. And you can nice like transforming. Watch what happens as you go from 0 up to 10 times displacement. And that's all the information that no one asked for that I think I had. Anything else coming up as you're working through? Just working. Yeah, you can check your computer. I maybe there's like getting. I know they were trying to like get all of them. They were. Yeah. Shoot. Also, oh, I just. I mean, that's just sometimes that's why the resolution works well. Like, it was there, but maybe not labeled, or maybe not noticed. Okay. Where this is graph that I was missing. Yeah, so right now it's not. But yeah, well, yeah, fix that. I mean, our first thing is just but I had part C first, so C A B, and I did oh yeah. This one has yeah, it was like the mod C. No, but it should be somewhere there. Okay. Yeah. Yeah. Oh, yeah. Oh, I see. Yeah. And you can like sometimes yeah, you can block it with that and draw. One with that. Well, I also yeah. Okay. So that would be why like yeah. Like in the very first like trying to get it to converge, the back converge is like it's not right. And the rest of it's all maybe right. Yeah, but just on that. That first like the first verification is going to be like crucial, but everything else after that is building on that. He's saying this is all correct choice. Two different answers. It's all correct. Who knows? Yeah, yeah, yeah. Oh, you can plug it in back. The same way that we have up here, where play that because you have seen the so yeah, two 13s and maybe rather a subset of all three. is that time? 10, yeah, we started at 10:10. It's over. So in this step where we're trying to figure out, I know we're out of time, but when we're trying to create that LU matrix of that K, it is this thing. Like we're just trying to find that left-hand side set of equations. So we'll get like a big diagonal pivot matrix, an 11 by 11 lower matrix, and then an 11 by 11 upper matrix. And we can use that to solve the two-step problem. But we'll do that Wednesday, or you can do it on your own, but however you want to do it. All right, thanks a lot.